Hey everyone, in this video I wanted to talk about some different formats for line integrals that are kind of common. It really is just the same idea of the basic line integral, but we kind of wind up adding up like different things when you actually take the integral. So, well, let's go ahead and just get started and you'll see what I mean by that. So generally speaking, the line integral looks something kind of like this. In this particular instance, the one we're interested in is really just like the most basic kind that we learned about a little while back, where we're going over a curve C. We have some function f, not a vector field, just a function, and we're integrating it with respect to ds. And well, maybe a little bit of interpretation of what that actually means might be helpful, and then it'll help us set up these other two kind of formats of line integrals that we can look at as well. So what does a line integral actually tell us? Well, if we have a curve C, something kind of like this, okay, so this is our curve C, then we have our function f that can act on this curve C, and our function f is kind of representative. I like to think about it as like a density. So like if you're looking at your curve C as being like a wire, we can think about the density of the metal in the wire as being f, because maybe it's not constant throughout the wire. And what the line integral actually tells us is, okay, so C, we're looking at this curve C. F gives us the density across this whole curve. And then S, this ds here is saying, okay, we're going to take this curve and chop it up into tiny little pieces, like so. And the length of one of these pieces is ds. So like right here would be ds. And so a line integral, what it does is it chops it up into all these tiny little pieces, evaluates f along the curve C to take into account changing density, and then it adds all those pieces up, which is why in a previous video I said that when f is just equal to 1, all you're doing is adding up all these little chopped up pieces, and then you just get the length of the curve out of it. All right, but maybe a little bit more fundamental question is, though, how is ds actually determined? Where does that actually come from? Well, in this curve here, we can kind of think about it as having a little bit of a, let's use some colors, kind of like a horizontal component or like an x component, like so. And then it also has to move upwards. So there's a little bit of a y component as well. And we're looking at like a really small scale here. So we can actually kind of think about this as being almost like a right triangle. And I can label this side here as a, I'll call it a dx. And then I'll label my horizontal or my vertical side as a dy. And what this means then is that ds can be thought of as being kind of like the square root of dx squared plus dy squared. And now when we're doing our line integral, we don't actually wind up explicitly using dx and dy, but there are integrals that we can set up that do use that. So that's really what we're going to look at today, is what happens when we focus in on this dx and this dy when we want to take an integral over our curve. But before we jump into that, let's finish up talking about what this actually looks like. When we integrate this, we have that formula. It's equal to the integral from a to b of f evaluated. Oops, I don't need a vector there because it's not a vector field. Evaluated at r of t times the length of r prime of t dt, where r of t, which I'm going to write as being equal to, it's got an x component to it in terms of t and a y component in terms of t, is the parameterization for C. I don't think I will ever not run out of room writing that word down. Okay. So again, intuitively, what winds up happening here is we're adding up the length of the entire curve and take into account some sort of density of our curve. But like I said, we can also do this in such a way that we focus in only on the dx's or only in on the dy's. And so when we do that, a lot of times it's really popular to see an integral written like this. We'll have the integral over c of f dx. And really all this means is that, okay, instead of adding up along this entire curve and following all of its ups and downs and in and outs and all that stuff, we're only going to focus on how it changes in the x direction. So because this dx here is really just equal to the length of the change in the x component, right? So it's really just kind of going along and saying, okay, we can look at all these little horizontal pieces like this and see how it's changing only in the horizontal direction, like so. And you wind up adding up all these little horizontal pieces like that, and really what it just winds up giving you is just a notion of how far or how long it is just simply in the x direction, like from this point over to this point. And then once again, we're able to take some density into account. And the way that we're able to kind of account for this, or at least be able to set up our integral, is actually quite similar to what we do up here. And what we're going to use is x prime of t, since instead of caring about this entire vector here, we really only care about the x component, how it's changing in the x direction. So that's what we're going to focus in on for our integral. So what we get then when we want to rewrite this in a way that we can actually use it is we do f of r of t, because we still want to restrict our function to our line. That's this part, and that doesn't change any at all. But now we're just multiplying it by x prime of t dt. And I do want to emphasize that this is just regular multiplication. It's not a dot product. We're not taking a length here or anything like that, because x prime is really, I mean, it's just a component of the derivative of r of t. So it's just a number, okay? So you don't have to do anything extra with it. It's just already exactly what you need it to be. And that is what we do when we have this written like so, when we only care about the x direction of our curve. So you can think about it as these integrals add up pieces only in the x direction. And once again, still takes that density into account from f, but you're only looking at the overall horizontal length of your curve C. So like from here to, well, like, I guess like right there. So it'd be kind of like that length right there is what gets added up. We can apply a really similar idea with the y components, and we can take the integral over C of f dy equal to the integral from a to b of f r of t times y prime of t dt. Because this dy right here is equal to the length of change in the y components. Just in that little piece that you focus in on for that little bit in the integral. So instead of adding up all the little horizontal pieces, now what we're going to do is go through and add up all these little vertical pieces. Like so. And because of that, that's why we wind up introducing that y prime. So these integrals only add up pieces in the y direction. So again, the main focus of all of this is really just that if you see this dy right here, this is the formula you're going to want to use. It's the same idea as what we started with up here, except ds takes this entire thing into account, this whole change along the length of the curve, whereas dx says, okay, we're only going this way, so we only want the x component of our derivative from our parameterization, and the y component says, okay, we only want the vertical part or the y component, and that is accounted for with the y prime of t right there. So these are the two really other important formulas that you want, and I guess I can put a box around this one right here, but you should already have this one from the previous video. So, okay. But I do want to kind of work an example, just kind of going through how we would compute each of these. So let's do that. So in this example, we are going to let our function f(x, y) be equal to 1, and let C be a piece of y equals, let's say 2x squared from 0, 0 to 2, 8. And we are going to evaluate the following. Our first one is going to be just the standard f ds. Oops, that should be over c. Our next one will be over c of f dx, and then we'll do the one for dy as well. Okay. Okay, so let's just go ahead and we'll start, I guess, by just identifying. Let's go ahead and we'll just start with A. So with A, what we want to do is we have our integral of f ds, and actually in any of these cases here, we need to compute the parameterization. So let's go ahead and do that. Because this right here is equal to integral from A to B, f of r of t, length of r prime of t, dt. So for any of these right here, we're going to need the parameterization. So in this case right here, we're looking at just trying to parameterize a graph of a function. And when we have that, we always let x is going to be equal to t, y is going to be equal to, well, 2t squared, which means that r of t is equal to 1 and then 4t. And our bounds on t are really just the bounds on the x values, so t has to be between 0 and 2. Okay. R prime of t is equal to, oh, I did that in that next line. Okay, I take it back. R of t should be t. This one should be 2t squared. Gosh, I just took the derivative right when I wrote that down. So we're going to have 1 and then 4t here. That's r of t. Then r prime of t is that right there. Okay, so now I guess all we got to do is plug these things into here. So we have the integral over c of f ds, which is equal to the integral from 0 to 2 of 1 times the length of r of t, r prime of t, which is root 1 plus 16t squared dt, and that can actually be integrated using trig sub. So I'll leave that one to you, but pretty much that's just how you set up this guy right here when you want to use ds for our integral. Okay, part B. For this one here, we have a dx, which means that we are going to use the equation integral from a to b of f of r of t still. So we're going to still need that parameterization. So we're going to wind up recycling this information here multiple times. And then we have x prime of t dt. Okay, so we've actually already parameterized our curve. We don't need to do all of that again. And we can just go ahead and plug everything in, I guess, because all the work's already done for us. So we have the integral from, or over c of f dx has to be equal to the integral from 0 to 2 of 1. There's nothing really to plug in here for r of t because it's just a 1. And then we're multiplying by the derivative of the x component, which is just, well, it's just that 1 right there as well. That's x prime of t. So we can just use a 1. So, and then we still have dt. t. And also that one is really quite easy to integrate. Let's look at part C. So now we're doing this with respect to y, and this is when we use the equation integral from a to b f of r of t, y prime of t dt. And we note that our y prime, we also already computed that, and that's going to be 4t. So we have the integral from 0 to 2 of 1 times 4t dt, which is, again, really quite straightforward to compute. So yeah, that's pretty much it. That's how we use these different formats here. Oop, I'm kind of moved it off the screen there. For these kinds of integrals, it all comes back to this idea of when you take an integral over a curve, it is some notion of adding up the length of the curve, but then at the same time taking into account the density of the curve that you're working with, if it's like a wire or, you know, some other sort of physical property that you're wanting to account for as you chop this up into tiny little pieces. So yeah, and actually, now that I'm kind of thinking about it, since we had the ones inside of these integrals here, since f is just equal to 1, in each one of these cases, what you're going to wind up with is this right here would wind up giving you, well, it gives you curve length. This would give you curve length because it's just a 1 inside of that integral. Now, if you take a 1 inside of this integral over the curve dx, that is just like the horizontal length or the horizontal distance that it crosses, right? So I guess I'd call it horizontal distance of the curve. And similarly, if we wanted to talk about dy, so we just have the integral over dy with a 1 in there is basically what that is. You get the vertical distance. And then anytime you've plugged in a function that isn't equal to 1, you're not necessarily going to get distance, but it is something that takes that distance into account. So anyway, that's just kind of the big idea of what you're working with there. And the mechanics of it really just come down to these 3 equations right here. You use whichever one of these is appropriate based on the setup of the integral. So, yeah, that's pretty much it. I'll see you guys next time.